All right, good afternoon, everyone. I appreciate you sticking around for the last session of the meeting. This has been a great week, and I'm very happy to have been here and heard so many interesting things about lunar geology, instrumentation programs, and other science cases. My talk title, Astrophysics from the Moon, a wide range of science cases, sounds very, very broad. It's in fact a little less broad than I might have led you to believe, because I specifically would like to talk about low-frequency radio measurements. We've, of course, heard a few other frequency bands or types of measurements that can be done from the lunar far side today. Low-frequency radio is our big thing. Now, I have tried to keep this talk very accessible to all of you, keeping in mind the diverse range of backgrounds of everyone here. So this should be a very friendly talk. And I just hope to give you a general overview of why we insist on going to the lunar far side as radio astronomers. There's a couple of obvious reasons why the far side of the moon is a suitable platform. The lack of an ionosphere, or almost an ionosphere, I should say, is very favorable at low frequencies. At Earth, the low frequencies are completely blocked by the ionosphere if you venture in the range of 10 megahertz and below. We are shielded from RFI. Hopefully, we remain to be shielded from RFI on the lunar far side. Of course, the increasing level of activity will provide some careful boundary conditions there. And it provides a stable platform. If you're thinking of distributed elements, the fact that you have a surface to put antennas on is actually rather handy compared to formation flying and the difficulties that come with that. And of course, there's a lot to be learned. So let me walk you through the science cases, starting close to home and moving ever further outwards. The first science case I would like to talk a little bit about is basically about the solar and heliospheric physics, specifically in the context of solar bursts. So these are accelerated clouds of electrons that are freed upon reconnection events in the inner corona of the sun, and they basically cause very strong radio outbursts as well by their moving outwards through the solar magnetosphere. Because of the dropping density with radius, we see these bursts manifest first at higher frequencies and only later at lower frequencies. And spectrally, their structure is quite extensively studied. You see an example of the spectrum of one of those bursts for the lower megahertz or so in the top right, and they have this typical banana shape. So they actually extend up to very much higher frequencies, like 80 megahertz or so. But they really extend into the lower frequencies as the blob of accelerated electrons moves further out. Now, there's many interesting phenomena associated with these solar bursts. I have to be a little bit quick, I see. I'm already talking way too much. But we are considering which kind of internal structure these electron bunches might have and how scattering through the dense heliosphere affects the shape and the positioning of the source we see in radio. So this is a whole interesting field and a subject of very active research. Some imaging of these solar bursts has been done as well, but on a very fairly rudimentary level. If you look at the beam sizes in the top three plots over there, you see that the source general size has been established, but not much about the internal structure. And to establish internal structure, we would need baselines of up to about 10 kilometers on the lunar surface if you look at frequencies of around 30 megahertz or so. One further is magnetospheric physics. This is closely related, but this time it's the interaction of the solar wind with planetary magnetospheres in the solar system, particularly of the larger planets, Jupiter and Saturn and the other outer planets. Jupiter in particular is a very interesting case because it exhibits a very wide range of behaviors in radio. There's long timescale radioactivity at very low frequencies, but at somewhat higher frequencies, so from 20 to about 40 megahertz, there are these very fast S bursts, and they exhibit a wealth of structure at very short timescales, as you can see on the top right. I'm sorry, the labels may be sometimes a bit hard to read, but these are sub-second timescales, and there's many different local phenomena going on, many different drift rates and electron subpopulations responsible. So mapping these and how these bursts are structured or substructured is obviously very interesting. And in this context, imaging these bursts and figuring out where these electrons are radiating within the Jovian magnetosphere is also very interesting. For this, we need quite a high resolution. I'm sorry, the red is not quite visible. It says 175 kilometers baseline. So at 30 megahertz, again, if you want to reach a resolution of 0.2 arc minutes, you need really large array sizes. But the advantage is that you don't need many antennas for this measurement, as it's quite bright emission. And with about 10 antennas or so, you can already do quite decent imaging. Moving on to exoplanet detection. So these are similar to magnetospheric detections done within our solar system, but now for exoplanets, so interaction of exoplanets with bursts from their host stars. This is suddenly a much more difficult science case to pursue. These emissions at these distances are, of course, considerably much more weak, and we also need to make sure we don't confuse them with the powerful background at these frequencies. So we need a modest angular resolution, but that means that the array needs to be extended, and you need a very large number of antennas, about 10,000 antennas. And so this is not a trivial case to pursue. So this might be the most difficult science case among the ones I'm presenting today. Quickly moving ahead because the time is going really fast. Next one is low frequency transients. Now, of course, transients in radio astronomy are a hot topic, have been since 2007 or so, the discovery of the first fast radio burst. And the pulsars have been the longest studied of these transient effects. So we have some pulsar detections at very low radio frequencies done from Earth at about 20 megahertz. That's the lower limit of any pulsar detection we've ever seen. Using UTR2, but that's a pretty powerful facility which has over 2,000 antennas involved. And most pulsars actually have their spectral peak at somewhat higher frequencies and rapidly drop in flux density at lower frequencies. So there might be different populations of pulsars that we are starting to see with these low frequency detections. So this makes it very interesting to, of course, survey the low frequency sky because they might have a steep spectrum and they might actually be brighter at low frequencies. But we know very little about this population as of yet. Regular pulsars do show occasional giant pulses, which are extra bright by a factor of almost 10 to the 6, more so than the regular pulses. And so those might be detectable at low frequencies, but we are hampered by dispersion of these signals. So any short pulse at low frequencies will be dispersed by passage through the interstellar medium. And that means the pulse energy is also spread out in time, and so you lose signal to noise and recognizability. Besides, observing pulsars requires a de-dispersion backend. You need to shift together your frequency bands and see where the pulse power is concentrated, at which dispersion it is concentrated, and of course also at which period, if there is one involved. Fast radio bursts, as I mentioned briefly, are the other interesting transient science case. So far the record for the most low frequency observation of any fast radio burst ever has been done by LOFAR, using only the core station, which is about 1,200 HPA antennas. And it has been observed down to 110 megahertz. And you can see the detection here. The TVs might give you a little bit of a better view on this, but you see emission concentrated towards the lower end of the HBA band. And so this is, of course, makes us think, there might be a lot more going on in terms of FRBs at much lower frequencies, but we are just not really good at detecting them. Again, you need to de-disperse here as well if you want to concentrate the pulse power in a single short range of times. Now, moving on to ever further away from home, extragalactic studies are a whole other field on themselves, mapping the sky at very low frequencies, basically. We have a few elementary results, but those have resolutions of about a full steradian, if not worse, and they are typically incomplete. And so having a low frequency facility that can tackle this task would be very valuable. There's a lot of things to be learned. We have extensive relic radio lobes from active galaxies that tell us a lot about the time history of activity of these central engines. These are, of course, this is the example for M87 done by LOFAR at 50 megahertz. So you see a very complex large structure. We need, again, arc-minute scale resolutions to make sense of these patterns. And that means that we need baselines of about 70 kilometers in length. At a frequency of 15 megahertz, so that's the upper end of this range. So again, this is not very easy to do with a localized array. Now, the biggest science case that we are really after is neutral hydrogen cosmology. It's looking at the very early universe in the 21 centimeter line. So normally that's at 1.4 something gigahertz. But because it came from the so early universe, it is very strongly redshifted to our instruments and to us. And so we expect to see a very unique spectral shape with a few wiggles that basically no other source in the foreground replicates this complex frequency structure. So to observe this, you do need a filled aperture of about 1,000 antennas or so to be able to study the spatial variation of this pattern as well. Not just the global signal, but actually how it changes over the sky and how the Fourier modes look, how the powers are concentrated. Out of all the science cases, this one also requires by far the most careful calibration of the array. You really need to know its frequency response. You really need to know its interaction with the local lunar regolith. And so this requires a lot of effort also for Earth-based experiments that focus on somewhat higher frequencies, try to detect the EOR signal, which is somewhere around here. That is also a big headache to deal with. So on the moon, this is also a very major issue. So briefly summarizing the numbers I've thrown at you over the past few slides, you see that the size of the arrays vary considerably according to the science case. But if you take the bottom one to be our top priority, if you say, let's say we have a compact array of about 1,000 antennas offering baselines of up to 200 meters, there are a few other science cases that benefit from it. They are not addressed perfectly, but they do benefit from an array like that. Particularly the solar burst and planetary magnetosphere case will draw useful information from this. And with some more effort, perhaps the pulsars FRB case as well, although they do require more processing that we expect than the neutral hydrogen cosmology case. So basically, this leads up to this concept that we've been throwing around, the DEX, the Dark Ages Explorer, which this is a very early render, so please don't take this as gospel. This is a first wild idea of how it might turn out, but we are exploring different design types. We need to have extremely lightweight antenna types, a packed aperture deployed close to a lander, but directly onto the lunar surface. And this system might be augmented by outrigger antennas to help it function in these other science cases that I have mentioned. So this might be close to what we need for several other science cases as well. But the neutral hydrogen case is by far our biggest goal. So later, Sonia will have a talk in this session, and she will be able to tell you some more about some aspects of the research in this direction. But that's where I'd like to keep it for now. So thank you very much for your attention. Where do I go?
I think we have room for a couple of questions.
Hi, Brian Day from NASA Survey. Can you talk a little bit about the efforts that are being made to coordinate keeping the far side of the moon as a radio quiet area?
Yeah, this is obviously a hot topic, right? So there are efforts underway. I have not been directly involved in those, I must admit, but there have been a series of meetings. I think the most recent one was in Milan in March, trying to coordinate on a global community scale which rules might need to be adhered to. The big step is not to convince all radio astronomers we know exactly what we want. We want a quiet, low-frequency spectrum. But how to arrange this in the presence of the multinational efforts to go to the moon and the commercial side of this as well. It's very hard to translate this into a set of treaties that are to be universally adhered to. But there are ongoing efforts. I'm afraid that's all I can say for these at the moment. But it's very much on our radar, absolutely.